not like actually. So not like actually a one-sided speech. So today the topic is itself the middle age casting to modern age casting practices. So what, how do we actually describe as a middle age castings? So I describe this middle age casting is till the year 1990, where you'll see I don't know how many people know about actually this molding machine. So Alpha 300 dual twist molding machine. The people used to say very popular in that time. And the most of the foundries are semi-automatic and semi-mechanized foundry. So most of the things would be handled in a manual way. And during those times, it was this methods engineer and the melting head were considered as the gods of the foundry. So this was a era I would say actually I described as a middle age the casting practices, and there were a transition from 1990 to 2000. Like 1990, when you see it's actually in that decade as a end, I would say around 1990 the shell core practices were started. That was new to India, so some companies started the practice of shell core, and then the automation so were taken up by many big companies. They actually started from manual process to manual practices to automation in molding lines, and in some few places it is in a melting line. So still there were some area like the core making and all were manual processes. And during that decade, so I would say the end of almost actually this after around 1995, this casting simulation software. This was actually this transition period, I would say. So happened from 1990 to 2000. So Indian foundry industry started to see some new things like automation and casting simulation software. Though it was very new that time, and there were some limited users, and there were some service providers so who offer this service. So you can hardly count the number of people who gave this kind of service that time. Then once around 2000, it was actually the new beginning all over the world, I would say. Though it was started in 1995, it's a 3D printing process, but the real the feel and experience came to India after 2000. The few companies started buying this 3D printing technology. That was actually a new era, I would say. So now I would say actually we were in a middle age till 1990. Then there was a transition period from 1990 to 2000. So in the transition period there were improvement, there were actually new things like simulation software and automation in a new core process. These were the things happened in this period. And after 2000, I would say we got a sand printing machine. So in Europe, it was introduced early, the 5 years before. In India, it came after 2000. So when at the time of 2000, there were two technology offered in a sand printing area. It was one is actually the laser cute. It is laser sintered core. They used to call it as. And after that, the binder jet. These are the two products introduced in the market in Indian market. So one is from the EOS GmbH Germany, and another is the Pro. That time it was a Pro metal. So now it is actually different. They were actually split into two, and the two companies are giving the service in Indian markets. So at present there are actually some one more company from China, and there are many upcoming players we can expect in this market, the 3D printing market, so sand printing market. This is actually after 2000, I would say this is a modern day casting practices. So the case we saw in the 3D printing and this simulation software. So at that time, this IIT Bombay, the Mr. Ravi from IIT Bombay introduced a AutoCast simulation software. It was cheaper and suitable for an Indian market, and it was available. So you can predict certain kind of a level of casting simulation. So not like actually other Magma and all, but still it was very much useful. And affordable by Indian industries and Indian foundry people. So I would say this is a modern era started from by seeing the new software and affordable at affordable price and 3D printing. So this is the things and 3D printing. So now I come to the topic of this modern era casting practices. So why the 3D printing is important and why, how it plays and how it's going to be in future. So in a 3D printing, so mainly the two technology were introduced. Now this one technology is absolute. So there are no places centering right now at Indian industry. You can hardly see the one machine is running in one big OEMs. So in the rest of the machine, you see it is like the binder jet technology. I think this is a technology would be more suitable for this core making and some small mold making. So even these technologies used for a big mold making. So we can say how this, where exactly this 3D printing technology suits and works very well. So my perception, so my opinion, so it is mostly for the large metal castings and some complex casting features wherever involved. So it is very difficult and hard to get a mold in a regular method, a regular core making process. So where this technology will work very well. And wherever the timeline is very short, so we don't have enough time to make up molds and do the iteration. So where this technology is very much applicable, so 3D printed sand technology, and how this beneficial and what way it's going to benefit Indian industry. I would say in a 3D printing cases, 3D printing sand 3D printing cases, it's going to be beneficial in design of a getting system. So getting system, how it's going to be useful in this getting system. Yes, when you go by the conventional way of making the molds, there were some limitation. So you have to stick to that limitation. You have to follow the limitation. Then only, so based on that, your getting system is designed. But concerns was how do you avoid the turbulence in the flow running channel, the filling system. That was a big challenge in designing the running system in any casting metal castings. Like even this aluminum, it is too risky, too actually highly possible to get oxides when metal is filled because of the turbulence. Even the magnesium casting, it is a high possibility of getting oxides during metal filling due to the turbulence. So these things are there. So this sand printings, your grading system can be very much optimized and your flow, because you don't have any limitation in taking the mold out from the draw direction. There is no limitation due to draw directions. So it will be you get a lot of design freedom in getting system. So your flow will be laminar flow, smooth flow. So the filling will be very clear. So that way, I would say the sand printing technology will help in a large casting and complex castings. And second things, this higher yield, because when you get a freedom in getting system filling system, so you can try to reduce the filling channels, size of the filling channels and the size of the feeding system, and even so. So when how do you can ask me how this is going to help you to reduce the increase the yield of the casting. See, so what is the best feeding system? You would say everyone knows in the foundry that a spherical shape would be the best feeders, which will feed the material to full efficiency. That case, in a 3D printing, so instead of your cylindrical risers, it can be designed a cylindrical feeders and risers. You can design it as a design in a spherical shape. So that will give you the best feeding to the casting. So and by designing the spherical shape, so you'll be able to reduce the total size of this feeding system and risers also. So this way, so the one is the optimization of this feeding system. Another one is the yield, the improvement in the casting versus filling system. So your casting weight will be better, more, and your filling channel will be lesser. So this will be helpful to increase the casting yield. And the third things, so like a resource optimization, I would say. For example, so when you want to make too many iteration in proving the castings, so that number of iteration can be reduced, so that your cost of the development part will be lesser. So this is how I see this 3D printing will be more helpful for the modern day practice foundries to reduce the cost and having a design freedom, reduce the recession. These are the things I would say so more beneficial. And uh, in the way of having a benefits, there are some challenges also in this system. So, like the productivity is still not comparable with the traditional way of making a mold. So that is one big concern. But when you consider the big molds, still it is comparable. In future, I hope actually this problem will be resolved, because the upcoming, there are many people working on this technology. They are trying to actually bridge the gap between the existing mold making rate, production rate, and with the mold making rate with the machines. So I hope actually the future will be completely different in this technology. And the second thing is it's not I would say not suitable for a high volumes casting. So mass production castings, like when you want to produce in lakhs and thousands, so the making the molds itself will take a long time. So this is I would say this is restricted to low volume and large casting, I would say. And that another things is mold cost, because this is the biggest concern. See, so the foundry industries are always in tremendous pressure on the cost front. And the recent the happening, like the US and the China trade war, and this COVID-19 things made a worse thing to the foundry industry. Like their raw material cost itself is gone up to 25% in some places. In some metal, it has gone up more than 25%. So whenever there is a price fluctuation in the raw material and even some old material, the foundry industry comes under tremendous pressure. So they because in industry ecosystem, when you see the structure, when you see the most of the foundry industries are the service bureau. So you can count this more than 90% industry would be the service industry, and the less than the 10% would be the captive foundry, which produce the casting for their own purpose. That scenario, so this industry always come under pressure due to the raw material fluctuation and uncertainty in the nature, like COVID and all. So it has made a big change, and I don't actually what will be the impact of Afghanistan recent spat. So there may be some impact in every industry in every country. This is what I'm expecting. So other than this, so this system requires highly qualified and skilled operators, and the high maintenance cost. This is the biggest concern in. Yeah,
Manish,
yes.
thank you so much. There's a doubt we have in the chat box by Dr. Guru
Yeah,
Prasad
yeah,
Rao.
yeah, yeah.
He's asking spherical feed system, how will it not be cylinder as it creates path?
How come?
1 second. Sam, can you help me here?
It says, how will it not be cylinder as
As
it
it
creates
creates a
path?
path.
Path.
Yeah, for spherical feed system.
The spherical speed system. So when you design your running channel, filling system, and feeding system, so you have to consider the draw direction. So that considering draw direction, your speeder and riser design would be normally in a cylindrical with a draft. Then only your mold will be can be taken out from the patterns. But in case of sand printing, so there is no limitation in removal, drawing of the molds from the pattern. So it can be printed, anything can be printed. So your shape will be, because the best feeding, the, the, the shape which takes a longer time to complete a solid, to become a solid, is a spherical shape. So which will be able to feed the material, liquid metal, to the solid part of the castings till last moment. That's the reason spherical shape is always, because see, finally your volume versus area, the modulus of the shape. When the modulus of the shape is very high, then you'll be able to feed the metal longer time. This is the logic. So you have to, people prefer to have a spherical shape, but because of the limitation in making the mold, they used to go for a next preferred shape of the cylindrical one. So this is the logic. I hope actually I have answered to his questions.
Yes, I think GP mentioned thanks. I think
Okay.
Neeraj has also raised hand. Neeraj, you want to unmute yourself to ask question if you have?
Yeah, hi.
Hi, Neeraj, we can hear you and we can see you. Please put across your question.
I want to know about the flow process. As you mentioned, you can know the how we can know during the molding. Yeah, casting process flow through the gate is a laminar flow, turbulent flow. How it will be? How we will know
See,
it?
Neeraj, yeah, Neeraj. So
Yes.
you have a simulation software nowadays, correct? So with the help of a support of a simulation software, you will be able to understand whether actually your flow is very smooth. Yeah, wherever actually metal goes and hit the corner, there should not be a swiveling motion action, correct? When there is a swiveling actually the action, so it is going to, the metal will be disturbed. When metal is disturbed, you're going to get a actually turbulent flow. This is what actually the laminar flow, the metal will be flowing smoothly without any interruption. There will not be any obstruction in between. But in case of turbulent motion, so when metal is flowing in the channel, so wherever it goes and hit the corner, there will be actually the flashing action happens. That flashing itself becomes a turbulence. So that turbulence creates the oxide in the metal. That will be the your slag in the metal. Got so.
My question is that what parameters I will feed in the systems, which will decide that flow is the laminar, turbulent, and that flow is suitable for my mold.
So
My question.
that's what your calculation actually give you the how much velocity should be there and how actually this if see in a regular mode,
Velocity depend upon the area.
yeah, of course. So you have all the calculation ready and you have a software support to actually counter this issue. But
On area
still,
of flow gate, which is the required
yeah,
material.
yeah, still you have actually limitation in a conventional way of making the mold, where when the molds are to be made, so you cannot avoid making the vertical sprue. So the sprue would be always vertical. When the metal is poured in the vertical.
So you've muted yourself, Maniraj sir. Okay,
Hello.
I'd like to interrupt here. We'll be taking more questions during the question and answer session. Please feel free to put across all your questions in the chat box, and we'll be taking them all during the end of the session. We'd like to launch a poll now before we hand over the screen to Samit. Could I have the first poll, please? Okay, there's the poll. Have you accessed 3D printing before? Your options are on the screen. Great. So we have a good number of people who have accessed, and then there is also a good percentage of people who are still new to the technology, but we are glad you're here because you're going to learn a lot. Great. Over to you, Sam.
Isha, I have not actually taken the subject of topology optimization. Let me complete that portion also.
Right, sure, sir. Sure, sir.
Okay. So sorry to interrupt you in between. So I have covered only the sand printing and how this topology optimization will help us, because I would say that topology optimization and this both the sand printing, 3D sand printing is a complementary process, I would say. See, so when you have a design freedom, so you have a freedom in a sand molding also. So this can work in parallel. So if you want to have a 100% topology optimization, then you should have a 100% freedom in making also. So this is a point I like to put up here. These two technologies are complementary each other. So I would advise everyone. So if you have a software, the topology optimization, you should actually definitely do the best methoding and running system and do the mold making with the 3D printing. Then you have to try the difference between the conventional way of making the getting the casting and 3D printing. So what could be the difference in the quality? There will be definitely the quality difference. And again, the topology, I would say, is scope in for a best topology optimization. Again, it's a large castings, and there are some other than the casting area. I would say the extrusion and the rolling and forging area having a lot of scope for a topology optimization. And the investment casting, mainly the last foam and the last wax casting, where actually the master consumable masters are available, where you can have a better optimization in a shape. So that means the topology optimization is nothing but a material layout. So you can actually place your material in better way, so that this process, the casting process, will be useful to adopt this technology, adopt this topology optimization easily in that process. So I would say the 3D printing master also the last thing, because there are master available from 3D printing directly. So like PU resins, PU polystyrene material, which can be used as a lost pattern master. So that is an option available. And even in SLA technology, there are some available materials which will be useful for making the master for the investment casting. So, and other than this, this optimization will be helpful. The topology optimization will be helpful for a machine tool industry and automotive lot. So here, the people, the foundry, the people who are practicing foundry in the foundry feel that the topology optimization will be the negative thing for them. But initially it may look like, but it's really not, because so OEM will be very particular. So in optimize their parts and reduce the weight, but that doesn't mean that. So that will be harmful to the foundry practices, because when you have a optimized shape and a material layout, so your rejection rate will be automatically reduced. So by reducing the rejection, so your efficiency and output also will be improved, increased. So topology also one of the things which will be very useful for this industry. So this way, I complete my speech. Thanks for the opportunity. Thank you, Isha. Over to you.
Thank you so much, sir. Okay, we'll have a poll now. We had the poll now. Great. Sam, over to you.
Yes, thank you. Thank you, Manira, sir. I think that's the last pointer which you mentioned is what we are trying to achieve as an Excel3D and divide by 0. So like looking at the casting industry from so many years, it is something which is neglected in the initial days with advanced technologies coming in, and there is less scope where people are trying to explore what new could be done. And we actually thought that this would be a good awareness webinar today to transfer this knowledge to most of the casting and foundry industry on how this could be looked in a different way. And I think you shared a very good thought on that. So thank you for that. So with that, I would like to just quickly share my screen and take you through my slides today. So hope everyone can see my screen now. Yeah. So from Excel3D, I want to thank everyone today for your time. And this is going to be an interesting application which we also are exploring as an Entop partner in India. And Entopology has shown good success stories in various industries, and this is something, casting foundry industry is something which we are exploring and how we can target and help this industry. So Entopology is all about designing without boundaries. And before jumping into Entopology, many of you might be very new to Excel3D. So Excel3D we founded in 2019 in India and in UK. We have offices there. I will not spend much time, but I will tell you what we do as an offering. So we are there in the space of academy and consultation, product development, where we have setup of carbon 3D printer in the UK for short batch manufacturing of end use parts. Excel3D Healthcare, we developed India's first N100 category reusable respirator mask during the COVID times, which is patented now. And in Excel3D system, we are partnered to Entropology in India. Hybrid manufacturing technology is something where you can retrofit your CNC machines with DED heads for metal deposition and machining at the same time. And Sigma Labs is for laser powder bed fusion melt pool monitoring system. So that's the overall what we do as an Excel3D. Now let's jump into Entropology, which is today's topic, where Entropology, there was a reason for Excel3D to partner with Entropology, because we have selected few technologies. We understood what Entropology's power is. So it's a next generation engineering design software. And it is different than the current BREP software is because it works with implicit modeling capabilities. So the things which are difficult to be achieved with CAD softwares, it is really controllable and very easily achievable with Entropology. So we're going to see the demo of the software as well today, but give you a quick glance of what Entropology is, where it has come from. So Entropology started in 2015, and they launched a platform called as Element in 2016. And that's where they see a huge potential. I've been following up with Entropology since 2016, when they were in the startup zone in Formnext in Germany. And from there, they have grown really drastically, with having a platform today which is funded by really good companies. They are backing up Entropology here. So Brad is the founder of Entropology, a very good friend. And if you see the industry and veterinaries who are from the Space Claim or from Autodesk, and also from like whoever who were in the CAD domain, they are supporting Entropology because it is something new and it is a future for how the design can be made. So the mission of Entropology is empower engineering teams to design transformative products. So there are softwares which are in the market, which can do such designs. We have seen so many parts like this, Topology Optimization, implants, but the way you can control it with Entropology is something which is not achievable by any other softwares. So these are some examples shown here as an image, which are good studies. Now, we all know about traditional manufacturing, like 30, 40 years ago, we had traditional manufacturing, but today in last 2 decades, there was a need of something new, which is what we call as additive manufacturing today. You look at computers, we have these old computers and now traditional computers, and we have now multi-core GPU computers. But in traditional design software, there was a loophole. No one has thought about doing something different. Everyone stick to BREP, but Entropology came as a platform and started thinking differently and how they can do things, and they started working with implicit modeling. Now, just a quick slide on helping you understand what is implicit model. So you have a traditional CAD software which shows boundary representations. We call it BREP, right? So you have surfaces, and a topology clocks is actually welding those surfaces together, assuming objects created as if they are homogeneous. And that is where we have a need of the data preparation software before we go to 3D printing to make it watertight STL files for printing. And on the other side, you have implicit modeling function for Entropology, where we show in boundary rep, you have a sphere, it has a certain equation. With implicit representation, you also have a certain equation. And implicit function is the mathematical function, which gives you exact value of that point in that whole 3D space. Now, things becomes quite difficult when we do such operations like Boolean unite of these two spheres. If you see, the equations goes really complicated, but it becomes much more simpler and it's straightforward when we work with implicit representation. So just on a theoretical note, an implicit function of a solid object, which is seen in a 3D space, if the point is giving a negative value, it is inside the object. The point is outside the body, it gives you positive value. And if it's on the body, it gives you 0. This way, you can actually have a good control over your software of your designing, and that's where it gives you a benefit of using Entropology as an implicit model function. Now, if you, most of you, if you are from design background and if you understand design softwares, then something what you see on this image, you're creating fillets onto the onto your design at the last step. It's quite difficult making some designs. What we see here, which are unbreakable geometries, are very difficult to do and time consuming, but Entropology does it very fast. Again, field driven designs where you can have your analysis data onto a object to get free form designs possible, and a remixable workflow. So workflow is something which might be new to a lot of people, wherein it is not, Entropology does not work mostly on how the software, these CAD BREF softwares work, but they have a boxes which you select and there's a workflow. But that workflow you can save, and if you have the similar kind of geometry and apply similar kind of application to it, you just have to import and the whole workflow goes automatic to give you the part out. I think Praneeth is going to show you some of our workflows in the next after me. Now, how does Entropology do this? So it can take CAD model, simulation result, test measurements, material properties into it, and we apply our engineering knowledge through workflows inside Entropology, and we can get outputs from optimized shape, advanced geometries, validation meshes, manufacturing data. So we can go from CAD to CAD, CAD to CAE, CAD to CAM as well. And a lot of people ask what file formats. So this is a slide which shows what file formats can be imported from CAD, and you see we can get back to step and parallel solid from Entropology again, and also slice data. So most of the industries who have adapted Entropology are aerospace and defense, automotive, medical, and consumer product. We've been partnered to Entropology from last a year, more than a year, and we have a very good success stories in India, right from aerospace. Medical has shown really good successes, and we have supported good amount of medical companies for the implant design side of it, and automotive companies, and also the service bureaus. The application wise, today we are going to talk about how we can do topology optimization and use it. We have a use case study where we created the part, and the whole journey Praneeth is going to share. But the application wise, we can do structural lightweighting, then part consolidation, material reductions. We have architectural materials, lattice texture, which are easily be done, and pattern making, texturing onto the consumer products, or even we have design automation, which we can do. Some examples, if you see, when you work with additive manufacturing side, mostly data becomes one of the biggest challenges, like especially in the medical domain. So what Entropology does, it takes any CAD format or any STL, whatever format you put in, converts that into an implicit model, performs the operations what we tell it to do, and at the end you can export in whichever way. But there are different ways. Even if you export an STL from Entropology, it does not have to be in GBs. It could be in less than 1 GB as well. Like we have tried and done a lot of testing on it. So it helps you create smaller file sizes, but also take an example of heat exchanger. This is one of the very good success stories for Entropology, wherein these designs are really difficult to make with any conventional CAD softwares, but with Entropology it becomes much more easier, and these actually gives a very good amount of performance. Like it gives a good performance as well. And if you see all this, the 20% faster, 60% lighter, it's all the advantages we see with Entropology. So coming to today's point, we have this complete story of a wheel hub, wherein we started with a original design here, which is these are casted parts, where we started here, but with Entropology we could make the part more, like it's not over engineered, but we could make it much more lighter and much more efficient. This is a case study we did for one of the student Formula 1 cars. So let's see how that whole story is. So from my side, I have been theoretically talking about Entropology, what it is. I will hand it over to Praneeth who will give you a quick demo about this part from how it started and how it ended. And after that is going to be Swapnil, who will be talking more on the manufacturing side and 3D printing side and how he made it and the patterns and how the casting has been done. And I would say that we'll take the questions at the end. So I will hand it over to Pranit now.
Thank you, Sam, for all the insights. We'll be taking a poll right away before Pranit begins. Can we have the poll, please? Which of these current bottlenecks in the casting industry would you like to eliminate by adopting 3D printing? Pattern making for complex parts, less scope for lightweight parts, lack of freedom for design change, or the lack of material optimization? I almost thought there was a tie between pattern making and the lack of freedom for design change. But it's okay. Great. So I think pattern making for complex parts is one of the bottlenecks that we would like to remove. The lack of freedom for design change is also one of the major bottlenecks that the industry is facing right now. Okay, great. Pranit, over to you.
Thank you, Isha ma'am. I hope my screen is visible and my voice is audible to you all. Good afternoon to everyone. So before moving on towards the whole specific the topology workflow, I will be going through a GUF of how Entropology, because it's totally a different software as if you compare with any CAD software. It's a step above it, and it's a software which bridges the gap between a normal CAD software and your imagination, or you can see a complex designing. So let's move forward. So this is how the screen of Entropology looks. It's a bit different from any other software, and it also doesn't operate on the same as Samisa already said that it works on an implicit modeling technique. So this is a horizontal ribbon which we have, in which there are various tabs, and each tabs consist of blocks. Blocks maybe we can call in normal terms as the features, but in Entropology we refer as them as the blocks. And the blocks specify a lot of information to us. And I will just show in short what features Entropology has. Like the Create tab has various, like the normal CAD modeling softwares, and it's much easier to create a CAD model in Entropology itself, and also import any kind of, as Samisa already have shown you, that various types of files can be imported and exported from Entropology itself. Similarly, there are some modeling techniques, and one of the key points that are creating various types of lattice depending on various volume, surface type of lattice, infill type of lattice, field-driven designs. As Entropology works on implicit modeling, so using mathematical operations, you can create your own block itself, and you can use this operations as you need. Similarly, there is simulation inbuilt in Entropology for static analysis, which you can refer, and we will be going through some simulation for topology optimization. And some utilities like exchanging various formats, like the formats in which we need to export. Like we can have a CAD part and we can export it into HTL, or we can have an HTL file, and we can we can export it into any CAD type of a format, whichever preferable. Similarly, there are some manufacturing for additive manufacturing techniques. There are some slicing techniques on the software itself available, so you don't need to go to another software for slicing, and some presets for some machines or formats like CSV, CLF, CLI, SSL, or Reynolds or US machine. So it makes our process much faster. Similarly, there's a beta version. Since the software is upgrading, you will find various new techniques to be found. And some additive manufacturing techniques and architected materials. We have already done some webinars on architected materials too. design analysis. You can also import your design FE analysis over here and you can work on it, or you can export your create your own FE analysis over here and export it over there. Similarly, lightweighting techniques, and today's topic, that is topology optimization, where we can have a topology optimization based on volume fraction, stress constant, displacement constant, or any other passive region constant or extrusion constant. Today we will be focusing more on a volume type of fraction constant, where we will be reducing the material and reducing the volume. So just to know about the just to know more about this, I will just show you all how easy what block system is. So going to the block system, you can refer, like normally we have a tree features in any other software, but in topology we call it as a notebook, and it's specifically notebook which helps us organize. You will see more further in my workflow, in which for the topology optimization, how totally it helps us to manage our design workflow, and in how easier and reusable the workflow is. So this is how the notebook is, and here are various section in which we can have, and adding a feature or adding a block, we can say, it's really very simple. Like I have a cube, I just click on it. So randomly, if you go in any other software, you need to have a plane, then you need to create a sketch, then you need to have extrude and extrude out, whichever option you need. But in topology, it's just a piece of cake. You just click on it and you can have the whole around data. And this is the block which I was saying, that each and every feature has a block, and the question mark defines us what are the properties, gives us a brief about everything, whichever data you need, and a comment box where you can just refer your comment, and you can share this workflow with any of your colleagues, and we can get any information we need, like what are the inputs also, and what does the input means also, and you can change it to any dimension you need. So that's how easy it is. And you can also, once you are familiar with this block system, you can search any block over here with the name, like you can just add a cube, so I can find a cube here too. So I will just show how easy it is to create and how fast it is, like creating a lattice too. I have an infill lattice. Okay, I have this. So that's a infill volume lattice, and I just drag down my body on which I need to have a lattice, what type of lattice I need, and just bring my input. So in a fraction of seconds, my lattice has also been created. So as you can see, section view of it. So that's how easy, and we can also find how much time, like it just took 173 milliseconds to create such a complex lattice. So that's how the process of topology is, and it helps us to organize properly. So before moving towards the whole topology workflow, can we have a poll, Shama?
Yeah. The poll question, please. And we had a really interesting question out there on the chat box. Thank you. Sorry, I can't stop. The poll question, yeah. Which of these features are most helpful for part making in the current casting process? Top opt for manufacturing, automated geometric reconstruction, design for additive manufacturing, and end-to-end optimization with reusable processes. We almost have a tie between top opt and end-to-end optimization with reusable processes. But yeah, I think topology optimization is for a win-win.
I think so. We are totally focusing on that today.
Topology optimization, correct. Then you're at the right place. Thank you. for your valuable opinion. Great.
Thank you all.
You can carry on, Pranit.
So this is how so before moving forward, as I showed the whole workflow and how it is, so you can see how totally I have organized the whole workflow, and it's very easier for me to just have each section. So this is how I have divided my plan of action, like what should be done. So from the first thing I'm doing is that importing my part. So as you can see, we can import any kind of parts. So there are some list of parts which we can import in Entropology and related to CAD. And if it's for STL, there's a STL format in which we can import other STL formats. So normally this part was already designed, so have imported. So you can recognize there are pieces and edges in this CAD part. So to work on any CAD software, we need to just convert this into an Entopology format. That is the implicit modeling we say, and it's easy to convert. We just select it and we have a implicit modeling. So you can see the difference now that as Samir sir had shown you that the top looks joints or welds the surfaces and the edges. So since it's a B-rep software, so there are edges and faces. So what does this edges and faces does that it gives us constraint in designing any type of a complex model. But in case of Entopology, where it converts into an implicit modeling, it gives us the ease to, like, as you can see, the whole body is now a single body, and we don't have any faces or any edges or any constraints to design it. So once that is done, so have converted the whole body into an implicit modeling, and now we are ready to go. So there are some steps, like some pre-process steps, where we need to just identify what we need to. So currently, as I said, we are doing a topology optimization. We need to reduce this part. So why to reduce this part? Like, this is an FA racing car part, and like, since the race cars need to be lighter but without compromising with its strength, overall strength, we need to reduce some material from this. And I will also show at the end how much material we have reduced and what we have achieved doing this. So once that is done, we separate out the parts. Like this is the main frame, then this is the bearing space where the bearing will be. So I won't be altering any with this, so I segregate this first itself. And once that is done, so this is the part on which we need to apply the topology optimization, as these are the points, like these are the points which will be having the wishbones over it. So we don't need to alter with it. So I'm totally segregating it differently. So it won't hamper, like the topology optimization won't hamper the holes also. So once that is done, we classify our needs according to our simulations. We are done. We continue with the normal FE analysis. Like we have a FE model.
Pranit, does it take this time?
No,
Does it take time to load?
just a minute. It might take a bit to restart.
Okay. Meanwhile, while Pranit loads his screen, there's been a technical issue. Can we carry on with Swapnil, and maybe once Pranit is ready, we can get back to the software part?
Yeah, I don't think it's going to take much time, Isha. because the workflow would be disturbed, Just 2 minutes. Let's see. Wait for 2 minutes.
Okay.
In the meanwhile, Isha, can we launch a poll quickly so that we have one more poll we can launch it now?
Yes, please. Let's launch a poll.
So, what are the current? Just a second. Let's just launch this. Yeah, current pain points when it comes to casting or metal casting. So I'm just launching it. Over to you, Isha.
This is the poll, the third poll that we're doing today. The current pain points for getting casting patterns of prototypes are longer lead time, higher prototyping cost, or limited design freedom. So we have limited design freedom and longer lead times as the majority. Higher prototyping cost also contributes, but not as much as the lead time and the design freedom limitations. Great. Thank you, everybody, for your valuable opinion. Pranit, are we ready?
Yes, you have opened it. You opened it.
And that reminded me of GP's in the crowd today. He always used to say it's a Murphy's law, Things should go wrong when
Yeah,
we're doing it.
GP is saying yes, we can see it. Shall we succumb to Murphy's law, or shall we take a
But
chance?
if it's going to take time, then we'll go to Swapnil then. Then
Yeah,
we
we
can show
can
at
come
the
back
end.
to you. Yeah.
Yeah, I think Swapnil, you continue, then we can come back again.
Sure, I'll just share my screen. Give me a moment. Is my screen visible? Okay, cool. So thank you everyone. We are here today. We're talking about casting. We're talking about topology optimization and 3D printing. Divide by zero. We've been here in this space past few years now, and we've been doing some work into application development and more or less small batch manufacturing with 3D printing. We've been part of application development in terms of casting and sand casting, investment casting, and various technologies with various companies right now. But currently, the discussion that we were having and the whole workflow that we were talking about, how we can move from this component to this, and what is the advantage in terms of time and cost saving, and how it can be done with the help of 3D printing, like further manufacturing. So we can make these either patterns, or we can make investment casting patterns, or we can make sand cores with 3D printing, or maybe different types of methods for manufacturing. But especially particularly with today's example here, we approached this with investment casting method, and with top up, traditionally this component could have weighed around 882 grams with aluminum LM4 kind of a grade, and with top up output, this is weighing around 435, so almost up to 50% weight reduction here. I think on this Praneeth will take up later on, but it's a huge I think material and cost saving for sure. and how then it can be used with traditional 3D printers and make it really affordable and quick. We're going to talk about that. So in terms of low volume casting patterns, we've seen we had this poll, but we have a lot of issues in terms of long production time from vendor, longer design validation process, higher cost of production, and then we have samples are not available for client or internal team meetings, and these kind of issues going on with with the team, and we've seen this happening. Typically, these kind of casting patterns can be made out of 3 technologies. You have injection molding kind of a technology wherein you pour in wax into a mold and make these kind of patterns, or you CNC these patterns through either wax or maybe metal patterns in case of sand casting patterns, or you 3D print these either patterns or cores. And all these 3 technologies are there in terms of manufacturing these kind of patterns. But when it comes to small batch manufacturing, this is one graph I wanted to share, wherein we talk about cost per part versus quantity. And if you look at additive manufacturing, formatted, this is molding maybe, and this is again your subtractive CNC machining. Between 0 to 150 components, your 3D printing cost can be much lesser compared to your CNC machining and your injection molded pattern making. And this is the area where we are focusing on as Divide by Zero as a company. And this is the area wherein we are trying to make this affordable. If it's not affordable to you, you've tried 3D printing, you should talk to us. We'll help you out here, and give you insight on how you can save, this cost. But this is where we are working as a company. So, in terms of casting pattern, in-house CNC manufacturing versus in-house 3D printing, like this kind of a pattern, which is already optimized with, topology optimized in some way. So CNC machining, this kind of pattern is taking around 20 hours because you have a lot of undercuts, you have a lot of tooling that is required. You're switching these tools continuously, and again you need a stock, a particular shape and size, and then you bring in together. With 3D printing, this is going to take 10 hours and very less cost. There is huge time and cost saving. Reason behind is I'm just walking you through. I hope my video is not lacking. Let's see. Okay. So basically, this is the component wherein you can see there are a lot of undercuts. This is again optimized, and this is 3D printing being done on one of our basic machine. This is time lapsed, a very fast running video here. But so once this is printed, this kind of component, optimizing this, something like this is very easy on Ntop, and that is something that can be done. But manufacturing side of this can be done with 3D printing. And as I said, you don't need any tool change here. You don't need any fixtures here when you're running this with 3D printer. So while doing this, we have also worked with certain investment casting patterns, wherein this was one of the bicycle components that we did for one of our customers. Again, huge cost saving, and these are made out of our standard FFF or FDM kind of machines, and there is a material that we use and there is a process that we follow for this. And this is again huge cost saving compared to other technologies like SLA or other wax kind of 3D printing. Here again, yes, similarly with sand casting patterns as well, we've been doing this. Here we've helped one of our customers who works for Indian Railways, and they had this different types of impeller blades to be tested for different angles, and for them there was huge time and cost saving, because getting a pattern in few hours was very important for them. Not only that, but we have also worked on core box manufacturing. When we talk about sand core box manufacturing, basically sand cores are required when you have complex geometries such as impellers. And again, when it comes to topology optimized parts, again, when they are complex, we can also use this methodology, wherein with a special blend of polymer that our machines can print, we can also develop these sand core box for cold core box method, amine core box method, and shoot these sand cores out of the standard amine core shooter that is available in the industry. And we have actually worked this out. and at least generate 200 to 300. So this was a sand core, box pump impeller for around 250 mm dia, and this is something which is possible. We've been running this through, and again, this is very, very cost effective compared to traditional, sand core 3D printing. Not only that, yes, with TopOpt and 3D printing, you can run different design iterations. You can print all those in one go and then just finalize the one and fit and test and run through. The kind of speed that this combination offers you is basically unmatchable, because the problem here is with 3D printing was cost or timeline, which we have reduced. The problem with design optimization, the process was longer, and many times, because the process is tedious, many NPD design houses choose to go for something, settle in between here, wherein it's possible for them to jump to something which is better optimized and better, manufactured, which has a lot of time and cost saving. So that is the power again here. Typical investment casting process wherein you have injection or wax molding. So how did we actually go from basically this pattern here to this kind of an output with the aluminum again investment casting was typically standard. You have molds to make these patterns, as I said, and then wax molds are made out of these patterns. Pattern assembly is done. You have slurry coating, you have stucco coating, and then you have complete mold, and then there is in autoclave you melt out the pattern, and the heat melts away this wax or internal plastic or wax, and then you have pouring, and then you have shake out or break out, and then you have casting patterns which are reduced and finished. But in terms of 3D printed patterns, when we are running, the process is similar. You 3D print the pattern, you do the assembly with wax as attachment agent here on the tree, here similarly directly. Then you have shell building, which is slurry and stucco coating again. And then you do dewaxing and burnout. So when you're doing a 3D printed or polymer based 3D printed component on investment casting, you do the burnouts, and you can also use chemical based dewaxing as well, that is required, and you have to run at least 2 to 3 different rounds of coating and basically shell building and dewaxing together. And then after chemical based dewax as well, just to ensure there is nothing left inside, we do gravity pouring and then knockout and finishing. Also, with the polymer special blend that we have, our ash content rate here on the investment casting part is less than 1%, which we have achieved. We've been working, especially in this field, with many customers, and this is possible. So as I said, if you are looking at that meeting wherein you want to understand more, you want to discuss your application, we have that link on the chat. You can connect, we can set up that one-to-one call with you. And if you're facing any issues, if you have tried this before, but it does not work for you, we can help you out and we can support you here. So not only that, but we've been working with latest high-speed 3D printers. Yes, we were working on FDM technology or FFF technology, filament-based. We're now also working with laser sintering. And one of the advantage, or one of the reason why we are still stuck to FFF or FDM technology, is because this technology is pretty affordable. But we are now able to run through high-speed machines which can print up to 10 times faster than traditional FDM machines, and also deliver you accurate components and great finish, surface finish on these prints. These are some of our customers when we talk about, and I can see some of you are already here. So thank you for being here. These are some of our technology partners for joint development programs that we run. So all this, what we have delivered or developed, which was not possible without the academia support that we have for research. And yeah, I'll come back to this, but over to you, Pranit. And if you have any questions, you can park, in the chat box. And Pranit, if you're ready, you can take it up, and then we'll come back to this, end slide.
Question and answer.
How we can move further. Yeah.
Okay. Pranit, are you sharing your screen?
Hello. Yeah, can you?
Yes, we can hear you.
Yeah, I can't share my screen. Full visible.
Can you try now, Praneeth?
Yeah, yeah. Yeah, now it's possible. Thank you. I hope my screen.
We can see you.
Yeah, sorry for that technical glitch. So just after importing our body that and segregating on which the board on which the we should apply the end topology or topology optimization, we just have a normal FE analysis based on that FE mesh. Then we provide some forces on which we should have force applied based on our calculation as the race car calculations which we have. Then the what should be the fixed constant and where should be the forced apply. So after giving this inputs to the blocks, we then just have the structural components we say, and that is then Entropology provides us a totally topology optimized part. And as you can see, it's a bit rough, so we can have a control over it depending on a threshold and also on the iterations. We can also have the control based on the volume fraction. Currently have given 0.35, so you can alter it according to as I said in the before. So we are focusing totally on volume fraction constant, so you can change it and you can have your own based on your need. You can have the volume constant, and or also you can change based on, so it gives the various degrees of freedom to control over your geometry itself. And once that is done, so this is some rough kind of a body. So once that is done, Entropology converts your body into a smoothened body, and we can have the smoothened body, and that's how the smoothened body is. And now we fully and union it with the whole set of constraint like the pivot points and the bearing space. And once that is done, our part is ready. So after our part is ready, we need to manufacture it, or we can take it to another level to optimize, or we can have FA and analysis on another software. So we can export it into any format. So once that is done, we have a mesh format over. We convert it into a mesh. So you can see how defined the mesh is, and we can have what type of mesh it is and the properties, how many face count we have. So currently this mesh must be heavy. So Entropology has a feature to simplify, as Samir sir had mentioned. We can have a control over the size of the mesh. So we can simplify the mesh by amount. It won't alter or it won't harm any with respect to your design alterations. It would just reduce the face counts and keep a proper amount proper.
Pranit, are you there?
Internet issue.
Yeah, I think he has a net issue.
Has it been raining badly in Bombay?
Not really. Anyways, I think that was the last part where we are showing the mesh, and from the mesh you can actually export it as an STL, or you take it back to the CAD, or you do slicing on it and you can directly print it. That's how it was there. So once this was done, it was the STLs were printed by Swapnil, and then we did the whole casting of the part which is there. The only thing which I am missing, I think, Swapnil, do you have the numbers where how much was the weight reduction on that?
Yes, I have it. Just a second. Let me just go back. I think it was almost 50% here on this. Yeah, here you go.
Yes. So yeah, that's how the difference was there between the two parts. And it is according to the forces. So it will maintain that efficiency of maintaining that forces which comes on that wheel hub, basically. Yeah, I think that's the whole process which we did today. So Swapnil, off to you now. You can continue with yours.
Yeah. So I think I covered almost everything. We just, as I said, we've been mentioning you about the form. If you think you want to understand more about Entop, you want to understand more about 3D printing side of it, you have tried this before, but it does not work for you. Other softwares, anything, any queries, any difficulties that you have, we would love to, set up this one-to-one discussion with you, our application team, and we set up a meeting with your convenience time, your convenient time, and we help you solve that. Also, I think we have some questions here.
We
There's
have
one.
the first. Yeah. The first question was for Maniraj sir itself, I believe. GP had asked about the staircase effect. Will it be reworked? Maniraj sir, are you there? Yeah.
Sir, I hear you.
What is this question?
Sam, I think it's a technical question. Could you help me clarify this, please?
Yeah,
I'm unable to see.
just read it. One second, I'm just trying to find it.
From GP at 12:31.
So how about staircase effect? It will be reworked, was the question from Mr. Guru Prasandra. Do you understand this, or maybe I can ask GP to give more clarity?
I just want to see the question. Otherwise,
Is it the staircase effect of the 3D printed part? What GP is mentioning, or how?
GP, if you're there, could you please provide clarity on your question?
I think so. The questions are in chat box. What is the question? Exactly?
Yes, a staircase effect, when you have the layers, which are laid on layer upon layer, whenever it turn or a slant sections of your casting or the runners, it is going to invariably have the steps which are going to come in the way of the flow of the melt pool, So would you rework them to so as to have a smooth flow, or you just leave it as it is?
Is this question from GP?
Yes.
Yeah.
Yes.
Good afternoon, GP. See, there would be a staircase effect. You are talking about a staircase effect, correct?
Yes.
Yes.
Yeah. So normally this printed course and even printed molds. So people used to do some kind of a coating on the surfaces of the flowing system or casting surfaces. So this because when the layer thickness is around a point, now normally in sand printing, so in case of the voxel jet and in case of X1, the layer thickness are made up to 0.25. In some cases, there is a possibility to reduce the layer thickness up to 0.15. So based on that, this thing can be taken care in the coating, mold coating. So you will find a smooth surface.
And then with the 3D printed part, I think we can do finishing, and then
Yeah, in 3D printing, there is a sanding and kind of this polishing will happen in a sand mold. So it is actually the simple mold coat will be sufficient to manage this issue.
Okay, thank you.
We have the next question from Chinmaya. Will there be anywhere to judge through Reynolds number from simulation for laminar or turbulent flow?
Turbulent flow.
Yeah, that I have to verify. Sorry, right now I don't have anything in my hand. So let me check and in my simulation software whether I'll be able to find this numbers, numbers to find whether it is in a laminar and turbulent. So let me check. So
sure.
And there's someone who asked about the software is free for Entropology. What I would say is it is not free, but yeah, there is a research version available as well. If you are a student or your college needs it, and there's a research version which is with an educational discount.
GP has also asked if NTOP can be used as a standalone 3D CAD software.
Yes, I explained that, but again, for everyone's knowledge, so usually when we have a complete workflow of additive manufacturing, or even from the design, you have a design softwares, then you have a data preparation softwares, and you go on 3D printing side, right? So Entropology is a good fit, which can be from CAD to data. It sits in between that. So depending on the application, you can actually design from scratch, but Entropology gives you more advantage if you have a current design and you can just modify that and do a lot of alterations easily in Entropology. So I would say that maximum time it has to be after CAD.
And one more thing, Isha, this is my answer to GP again. Yes, mentioned in the chat box, it needs post processing. Mr. GP, this is see, when the molding process, when you compare with the green sand molds, so definitely there is no post processing. So we are not comparing this process, 3D printing, sand 3D printing, with a green sand mold process. Most of the core sand process, hard mold process, requires a coatings. So it is similar to that. So you don't need to go extensive finishing and the post processing requirements. So it is comparable with the process which is being followed in industry for any core sand and a hard sand course. This is comparable.
Thank you, Maniraj sir. Swapnil, I believe the next question is for you. What were the shrinkage allowances in the investment process?
So basically, it's around 1% to 1.5% that we usually keep. Again, shrinkage allowances. That depends on the process, but yeah, 1 to 1.5% is what we usually consider on this.
I think the next question is also for you, Swapnil. How to get good surface finish from first layer of printing and the factors which cause this effect.
So I think it's called elephant foot effect. And if you're facing this, you can use something called as brim on your slicing software. So that gives a first flat layer, which is an adhesion layer, and then post that your print starts, and then later on, after your print is done, you can separate out the brim, and you have no elephant foot effect there. So yeah, that can solve your problem. What's the next question?
I don't know who is Chinmay asking this to. So you are from team Divide by Zero or Excel3D.
So there are two different teams, but we work together for this project.
In fact, all of us believe in helping and adding value to casting and investment casting, sand casting with the technology. And that's why we have Maniraj sir, we have Samit, we have Isha, we have me from Divide by Zero and Excel together. And obviously Maniraj sir from Hero MotoCorp, he is an experience in casting industry.
Yes, so all efforts we wanted to share here is to relook at the casting and foundry industry on how advanced manufacturing, like additive manufacturing, or what can we do differently to explore this industry. And this is one of the topics which we found that, it is a good thing that people can start thinking about it as well, because looking at a 3D printing side, or looking at, say, FFP technology, which Swapnil mentioned, the pattern making cost has gone down, and that is one of the biggest pain which is there in the casting industry. So if there's a clear scope that when there is a short batch which is required, we can definitely go for this technology using of additive manufacturing. And also with topology optimization, you can actually make your part more efficient if you have the short batch manufacturing, which can happen in casting. So that was our effort today as Divide by Zero and Excel3D. And Mr. Maniraj is an expert in casting, and he put a very good limelight on old traditional ways to how new ways. I think to end up with, I had this personal question for Mr. Maniraj. Sir, it is because you have this immense experience with Bajaj and Hero MotoCorp working in the casting field from so many years. How do you see Indian casting and foundry industry moving towards accepting this advanced technologies?
Samit, so my opinion, Indian industry especially foundry industry, are very much cost sensitive. So we are just way behind the developing countries. It's taking a longer time to adapt new technologies in our industry. So it is there, but the last 5 years, I'm seeing there are tremendous changes, and the mindset of the people are changing. So in coming years, so there will be an adoption of a lot of new technology, and this 3D printing industry, as well as this material layout optimization will take place in a different way, in a different level. So definitely there will be a huge opportunity in Indian industry, but at present, so till I would say the 2015, the adoption rate was very slow, comparing with US and Europe and China. So now since people are got convinced that okay, this we can take the advantages of this new technology. So I hope actually in upcoming years there will be a good adoption rate in both the 3D printing area and optimization, material layout optimization.
Thank you, sir. Thank you so much. Yeah, Isha. So I think thank you everyone from my side. It was really interesting to see all of you giving your time here. Thank you for your
Taking
time.
time out to join us for this webinar. We have gone a little beyond our expected time, but that only proves that this session had been really insightful and helpful for you guys. So I expect it's been a very helpful and interactive session for you. Extending our gratitude to Maniraj sir for taking time out and sharing his insights for this session. The link to book a one-on-one session with our experts is there in the chat box. Please feel free to book your session in case there's any doubt you need that's not being cleared, or if you need something that our experts can help you with, please book a slot for yourself with our experts there. Thank you so much for joining us today.
Yeah.
And Swapnil, I think you have an employment request from somebody.
Sure, you can write us on this
Not
email.
opportunity, it's a request from somebody. You can cater to that on a personal level.
Thank you, Swapnil. Thank you, Sumit. Thank you, Isha.
Thank you, sir.
Thank you, sir.
You, everyone.
Thank you so much.
Thanks everyone for joining in. Thank you, sir.
Thank you so much, everyone, for joining us.
Thank you.
Thank you.
We are going to come up with more of this. So thank you.